Welcome back everybody to Geology 101. As you can see, this unit will be about glaciers. And before we get started, what can you expect to get out of this unit? Well, the first thing is to be able to describe where glacial ice is on the surface of the Earth. You could explain something about how glaciers form, what they're made out of, and how they move, locomotion, how that process works. You could identify different types of glaciers, and you could tell me where you could find these on the map, what is the relationship of one type to another, and then finally you could tell me something about the role that glaciers play in erosion, in shaping the Earth's surface. So for our first section, we will start with the Glacier Basics. So what actually is a glacier? A glacier is going to be some body of permanently frozen water, right? Permanent ice year-round. And these tend to form in largely the same way no matter where you are. You have an accumulation of snow, snowfall, and it's going to be in some sort of region where there's more snow falling than there is snow melting. So snow continues to fall, and at first you have just a little bit of snow. There's going to be a lot of air in between the little snow particles. It's going to be less dense, lighter, fluffier stuff. But as it starts to accumulate larger and larger and larger amounts, you start to get compression, which leads to recrystallization, something very similar to what you see in metamorphic rocks. Now, if we look at our diagram here, right, we can see where this might happen. So up here, closer to the top of the mountain, is going to be where we get our net accumulation of snow, right? More snow falling up here. And as you move to lower elevations, actually here we have more snow melting than snow accumulating or falling, right? Total ablation. The opposite of accumulation, which happens higher up. And as this glacier moves down, and we'll talk a little bit in more detail later about how it moves and why, it starts to melt a little bit, starts to break off into icebergs in a process known as calving. So there are two main types of glaciers that we have to talk about right away. So some glaciers are found high up in the mountains, like in the Andes Mountains in South America or in the Alps in Europe. And these are actually named alpine glaciers after the Alps where they were first studied and documented. But there are these other kinds of glaciers, like the ones you see in Greenland or Antarctica. And these can more properly be called ice sheets. And actually, most all the ice in the world, about 98–99% of it, is going to be in these large ice sheets. But if you look at our images here, you can tell right away, right? These ice sheets tend to be very flat, not very interesting in terms of the terrain itself, whereas the alpine glaciers, mountain glaciers, and valley glaciers tend to be a lot more interesting in terms of the geology, and that's where we're going to focus a little bit more for this unit. So if I showed you two different images, and I told you these are different places in the world, and then I asked you which one is the alpine glacier and which one is the ice sheet or the continental glacier. You would look here and you see all these mountains. You know this one has to be alpine, like the Alps. You see terrain like this that's relatively flat, not rugged, no mountains. You know this must be the ice sheet. So what's that one piece? We talked about the distribution of glaciers and of ice on the Earth's surface. Well, it tends to be about 10% of it, like we've covered. Most of that is going to be in Antarctica and in Greenland as these big ice sheets, a small percentage in the mountains and in the valleys. This is actually down from a high of about 33% during the last ice age. So the last maybe 2 million years up until about 10,000 years ago of Earth's history. These are going to have the majority of the world's fresh water locked up in them. It's not as accessible or available as you might think. And importantly, the way that they move is really interesting. So let's take a look at our diagram here. Now we have our accumulation zone higher up in the mountain, more snow falling than melting, and our ablation zone. So lower down, it's going to be a little bit more snow melting than actually accumulating here. And right in between them, we have our equilibrium line. Now, if you imagine that we suddenly increased the amount of melting here, well, this equilibrium line would actually start to move up, and the glacier, even though the individual particles are flowing down like this, would start to recede. It would look like it was moving back up the mountain. On the other hand, more snowfall, more precipitation, this line would move down, and the glacier would be advancing. But keep in mind, the motion of the particles themselves is going to be driven by gravity. Now, the way this actually works the top maybe 50 meters or so of it is going to be a little bit closer to loose snow that you might find on the ground. It's going to be a little bit more brittle. But once you get into the center of the glacier itself, it starts to flow. It starts to behave a little bit more like a liquid, like plastic flow. This is actually the same thing that happens in the mantle of the Earth. We have something that is solid, but because of the conditions that it's under, it is able to flow very much like a liquid here. And actually the fastest is going to be here, closer to the surface, but in the middle of the glacier. Once you get too far down, too close to the actual bedrock surface here, there's so much friction that it actually starts to slow down the glacier. So a little bit like with a river. Fastest flow is going to be closer to the middle, not at the top and not at the bottom of the glacier. Now let's look at one last example here. We have our glacier moving down the mountain. The fastest part of it is going to be not at the bottom, but not at the very top either. It's going to be, well, the velocity curve is a little bit like what I'm doing with my cursor here. The fastest part is in the middle of the glacier, but towards the top. And if we actually cut out a core, right, if we took this part of the glacier and just took it completely out and looked at it, what would we see? We would see fresh snow at the top, older, more compacted snow in the middle, not completely loose and airy, but not completely recrystallized either. And once we got below a certain point, there's so much compression that the snow comes together and recrystallizes, forms these interlocking mineral grains, and forms the glacial ice. Now let's take a moment to zoom out here. Where are all the glaciers in the world? And if you immediately thought of places like the Arctic and the Antarctic, you would be mostly right. We have a lot up here in the Arctic, including the Greenland ice sheet and over on the west coast of North America. But there's also quite a few glaciers that aren't near the poles at all, right? We have glaciers running up and down the Andes Mountains, in the Alps, and over here near the Himalayas in Asia. In other words, you can find glaciers in some capacity at pretty much any latitude all over the Earth, although they do tend to form at the more extreme latitudes north or south. So for the sake of comparison, I've included these two diagrams here. We have today's continental and sea ice here, looking at the northern hemisphere of the Earth, so not Antarctica, other side of the world here, and what it might have looked like whenever you had the maximum glaciation during the most recent ice age. And important things to notice here. First, there are no glaciers per se at the North Pole. Why? Because there is no continent at the North Pole. Instead, what you have is a lot of sea ice. It's going to be not nearly as thick as something like a continental ice sheet, but it would be covered in ice nonetheless. It's going to be ice floating on water. And another important thing to notice here, if you look at the amount of ice sheet that was covering North America, you can see that it extends a considerable distance into the United States. In other words, the surface of the United States, the terrain, the way it looks today for everything from maybe Illinois or Ohio upward, was all shaped by an enormous ice sheet. It has a tremendous impact on how the continent looks today, North America, because geologically this was very, very recent, including, well, scraping off a ton of the sediment cover up in Canada. Okay, so let's zoom in a little on the part of the world that we know best here in North America. So how are glaciers distributed here? As you might know, might imagine, a lot of them are concentrated up in Alaska, up in the northernmost parts of Canada, over on the coast of Greenland here. And you ask, well, why isn't this colored in? Because this is an ice sheet here, and we're specifically talking about major mountain glaciers, alpine glaciers for this slide. And if we look, there are glaciers up here, the Cascadia mountain ranges, higher elevations over here in the Sierra Nevadas, and actually there's some included in Mexico. And I wanted to include a couple questions here just to get folks thinking. So why are all the glaciers in the United States concentrated on the western part of the country, right? And you could say, well, that's where the mountains are, but what's the deeper reason behind it? And second, these glaciers that we see in Mexico are at the very top of huge volcanoes. What type of volcanoes do you think we would find down there that have this glacial ice? Okay, So we're going to zoom in on a certain place. We're in the mountains. We have glaciers, looking at alpine glaciers here. And this is what it might look like. Now, before we get to the part where we assign names and vocabulary terminology to all of this, we're just going to look. So we have the very top of our mountain here, seems to be covered with a sort of cap at the very top of ice, and it feeds out into these other glaciers, right? So you might say that this is our source, and these are the outlets for the ice, kind of relieve all of the ice coming off of the top of the mountain here. So we might have glaciers that are at the top of the mountain, some that are in these circular shaped, almost bowl-shaped regions here, some inside the valleys, one that looks a little bit like a bulbous lobe or a foot here, and another one over here. Looks like the ice has finally moved down from the mountain to start spreading out. And then finally we have these places where the glacial ice meets the sea. Alright, now we'll introduce the vocabulary, our terms. We're going to have cirque glaciers, valley glaciers, ice caps, fjord glaciers, and Piedmont glaciers. So the first kind we'll look at are those bowl glaciers, right? It almost looks like somebody carved out a chair here or a seat. We can actually see the bowl shape of it. These are going to be our cirque glaciers, right? It's going to be here in that original diagram that we looked at. So these are going to be named for the cirques. Those are the bowl-shaped structures that they occupy, tend to be found higher up in the mountain. Now, what about this glacier here? Well, we have our mountain on one side, mountain on the other, and this glacier is going to take place in the valley. So these are our valley glaciers found here, here, and actually here as well on our diagram. So these are going to be our streams of ice flowing through the valley, easy to remember, and, well, it's going to be confined by the valleys on either side, and over time they actually carve these valleys out, tend to shape them into these sort of U-shaped valleys and canyons. Alright, now what are we looking at in this image here? Well, this actually is going to be the very top of our mountain here. And even up above, right, capping the mountain, so to speak, is going to be what is called an ice cap, right? So this is going to be our original source for all of these other glaciers, valley glaciers, fjords, as we'll see, Piedmont glaciers, all of the other outlets. Tend to be more dome-shaped. This is going to be at the very peak of the mountain, and they tend to collect in these high elevation catchment areas, get a lot of snow, and drain into the outlet glaciers. Now, what might be going on here? Okay, well, we have our iceberg first. We can spot that. It looks like we have a body of water here. We have a valley with a glacier in it here, and right as it meets the water, it starts breaking off into icebergs, right? Call this calving. So this is going to be our fjord glacier. This is what happens whenever you have a valley glacier that flows so far that it actually reaches the sea. It's going to calve and produce numerous icebergs as well. Okay, and our final type of glacier. We have our valley glacier, which we can recognize here. And okay, we're moving from higher up in the mountains, we're moving lower, lower, and lower until we finally have ice that spreads out into this kind of bulbous shaped lobe or foot on the flatter plane. So this is our Piedmont glacier, like here in the diagram. So these occur whenever you have a steep valley, spills out into a flatter plane. It's going to spread into these bulbous lobes. Glaciers do a ton to shape their environment, and in the next section we'll talk about how and why they do this.